So I'm asked here to calculate the pH of this solution. I look at that and I notice a potassium, which is a cation, and that tells me right off the bat that this is a salt. Okay? What is it a salt of? Well, it is going to break apart, and let's see right what it does. It will break apart 100% into K plus and the rest of everything, C6H5 minus. Now this, with the H attached, is the acid. And I know it's the acid because of two things. It has an H right here, okay, and I've been giving you a Ka of it. Just want you to give a look at what it is. It's an organic acid. It looks like this. It has, and you don't need to know its structure, but I just want to give you a feel for it. Has alternating single and double bonds. It has an O and an H, and it's this H right there at the top. I'll circle it in red. It is that H that behaves as the acidic proton. All the other carbons have H's, but those are attached way too tightly to be donated. So here is a weak acid. Look at how weak it is. It is a super weak because it has a Ka value of 10 to the minus 11. Now, whenever you have a really, really weak acid, its conjugate base will be correspondingly stronger. The weaker the acid, the stronger its conjugate base. So this guy right here is actually a fairly significant weak base. Okay, it is a pretty good proton acceptor. I put that minus there because after I take off the H plus, it's negatively charged. So the acid is called phenol, and then we lose its hydrogen and it becomes this conjugate base, and now I have a salt containing it. Now what do we know about these salts? It's a one-way arrow. They 100% dissociate into its ions. So I will do an ICF table because it 100% 100% dissociates. That's the word we use for it. I started with a 1.2 molar solution. Before it dissolves, I don't have any of those ions, but it dissolves completely. So I end up with none of it in its combined form, and I end up with 1.2 molar in the F line, the final one. It's all said and done. Now you'll get to where you don't have to do that little table there, but I want to show you how you know the concentration of the ions present. Now we've established, as we have worked with salt solutions, that a 1A or a 2A metal is neutral. And I have just talked you through the fact that this anion is a base. It is the conjugate base of this very, very weak acid. And as a base, it will do the base thing. What is the base thing? Well, bases are proton acceptors. So we take the OC6H5 minus, it's in water, and it will, as a weak base, accept a proton and become HOC6H5, and the water becomes OH minus. It will have an ICE table under it because it's an equilibrium. I will take the concentration that I got from my first table and put it right there. I have none of this yet. I do have a little bit of this, right? 1 times 10 to the minus 7, but usually works out just fine to call it a 0. So then I will consume and I will produce, leaving with 1.2 minus X, X, and X. Now to the right, I'm going to go ahead and write the KB because this is a base. I will write the KB expression. KB is HOC6H5 times OH minus divided by OC6H5 minus. A lot of times students will leave that step out and they'll just start plugging things in. Recommend you keep doing it for a while because eventually we'll make some changes to our reactions and you'll not know what to do with the change. But let's see, what's KB? I didn't give you KB, I gave you Ka. So to get KB, we're going to take 1 times 10 to the minus 14 divided by the Ka of 1.1 times 10 to the minus 11. I will plug in from my table the values I see in the E line. Now 1 times 10 to the minus 14 divided by 1.1 times 10 to the minus 11 is 9.1 times 10 to the minus 4. Notice that's a pretty decent base KB value. So that is equal to x2 over 1.2 minus x. And let's try the assumption that x is very small, much smaller than the 1.2 to make it easy to solve. And solve for x. It would be 9.1 times 10 to the minus 4 is times 1.2 is equal to x squared. So we take the square root of both sides, and we will get x is equal to 0.033. Now what is x? X is the OH minus concentration. So if we take the negative log of 0.033, we will have POH. And that is equal to 1.48, and the pH is equal to 12.52 when I subtract that from 14. Now don't finish without making sense of this number. That's a pretty decent pH of a base. This is a fairly strong base. I mean, it's a weak base, but you know, it's not a bad value. So getting a high pH with this pretty high concentration is expected.